Welcome back. So we finished section 4.3. Let's do a quick optimization problem. So section 4.5, 4.7. Oh no, sorry, I skipped L'Hopital's rule. All right, so L'Hopital's rule. For L'Hopital's rule, let's do two problems. So let's try number 9. So this is section 4.4. All right, so we want the limit as x approaches 4, x squared minus 2x minus 8 over x minus 4. So if we plug in 4, we get 0 on the bottom. If we plug in 4, we get 16 minus 8 minus 8. You get 0 on the top. So this is a type 0 over 0. So we could use L'Hopital's rule. So this is the limit. As x approaches 4, take the derivative of the top, 2x minus 2. Derivative of the bottom, 1. Now try to take the limit when x goes to 4. 2 times 4 is 8. Minus 2 is 6 over 1. The answer is 6. All right, another one. Let's see, 20, 31, 43, 43. So let's try number 43. That's a product one. The limit as x approaches infinity of x sine of pi over x. All right, so as x goes to infinity, x goes to infinity, and pi over x goes to 0, sine of 0 is 0, so this is a limit of type infinity times 0. So the technique is to write one of the terms as a fraction. So write it like this, sine of pi over x divided by 1 over x. X is the same as 1 over x. Right? Writing it a little nicer, x is 1 over x. Now we could use L'Hopital's rule, because now it's of type 0 over 0. So take the derivative of the top and bottom separately, use the chain rule. Do not forget the chain rule. It's always important. Limit x goes to infinity. So it's the cosine of pi over x. But now the derivative of the inside. Pi is just a number, like 1 or 2. So don't just multiply it. Just keep it there and multiply it by the derivative of 1 over x. In other words, it's negative pi times 1 over x squared. Or pi times negative 1 over x squared, maybe more accurately. See the derivative of 1 over x? Negative 1 over x squared. They almost cancel, except you're left with the pi, right? So it's the limit as x goes to infinity of pi, the negatives do cancel, cosine of pi over x. All right, pi over x goes to 0, so in there we go to 0. Cosine of 0 is 1, so it's pi cosine of 0 equals pi. So the answer is pi. All right, next let's cover a optimization problem. Let's see, 13, 15, 19. All right, so let me try a box one. The field ones are pretty easy, and I'll leave those to you to try. 4.7, let's try number 19. All right, so 1,200 centimeters is available to make a box. All right, with a square base and an open top. So x by x, and the top is, the height is y, so it's x by y. That's how you get the square base there. And the material is supposed to equal 1,200. So 1200 is the surface area. Don't forget open top, but the base is not, but there is a base. So what's the area of the box? X squared is the bottom, the base, and then there's 4 sides all equal, 4 xy's. Yx, 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 4 sides. Okay, we want to maximize the volume. X by x by y, x squared y. Okay, looks like it's easy to solve for y, and then we'll plug it into here to get rid of one of the variables. So let's see, 1200 minus x squared over 4x is equal to y. So that means the volume is equal to x squared times y. 1200 minus x squared over 4x. All right, simplifying this a bit, this is equal to, so 1/4, and then x squared over x is just an x, so just multiply through by x. So let's see, 1200 x minus x cubed. All right, so how big can x be? Well, x can basically start at, it's really open 0 since you wouldn't want to let x be 0, but the x is going to cancel out. And the biggest x could be is when x squared equals 1200, so that would be radical 1200. Because otherwise, y would become negative, which we don't, would become 0, which we don't want either. So these are our theoretical endpoints. All right, take the derivative of v and set it equal to 0 to get the critical numbers, and you would get 1200. There's a 1/4, which you could just take out in the front, minus 3x squared equals 0. Divide both sides by 3, take out another 3, and you get x squared equals 400. So x is 20. All right, so you can make a little t-chart now of x versus the volume, and you could put 20, the critical number. Then you can put the 2 endpoints, 0 and square root of 1200. Both of those will give you 0, and the 20 will give you the maximum. So let's see. 20 is x, right? So we just need to find y. So to find y, we would go right here. So let's see. 1200 minus 20 squared divided by 4 times 20. 10. So y is 10. All right, so y is 10. So the box, the volume of the box will be 20 by 20 by 10, which is 4,000, clearly bigger than 0 on the 2 endpoints, so that has to be the optimal solution. All right, and let's do an antiderivative. 4.9. 61, 65. Let's try number 65. So let's try 4.9, number 65. So suppose you're given the velocity function, which is 2 cosine of t plus 4 sine of t, and s of 0 equals 3. Okay. And the goal is to find the position function. Find s of t. Okay, so we have to take the antiderivative of the velocity to get the position. So s of t, antiderivative of cosine is sine, So the 2 just comes out and multiplies. It's a linear factor. Integral of the antiderivative of sine is negative cosine, so it's negative 4 cosine of t plus a constant of integration, an antiderivative constant. We're given that s of 0 is 3. So 3 is equal to 2 times sine of 0, 0, minus 4 times cosine of 0, which is actually 1, plus c. So the 2 times 0 goes away, the negative 4 add to the other side, 7 is equal to c. All right, so the position function, the final answer here, is 2 sine of t minus 4 cosine of t plus 7. All right, so hopefully I didn't go too fast here. I guess this is the speed I would go if I didn't have students asking questions. And of course, on the video, you can't really ask any questions, but you could pause it and try to fill in the details on your own a little slower, if need be. All right, so I hope this was helpful to you guys. And any questions, send me an email. I'll try to check the email tonight and tomorrow in case anything comes up. All right, have a good night, everybody.